This is the third part for the presentation 8, where I'm discussing the supervision, management and maintenance layer. And in this part, I will be talking about how we can work with semantics, the semantic hypothesis and semantic data. I won't be showing any implementation here. Rather, this is just a description of how I myself accomplish these things. And I will be using binding as a linguistic phenomenon as an example. Now I don't remember if we already discussed it at some point, I think not. So here is a simple illustration of what binding is about. So in the first sentence, when we use a reflexive pronoun like himself, we can create a sentence where the two referential expressions, John and himself, must refer to the same person, the same entity, the same male person. And sentence 2 shows that it has to refer to John, the subject, in the same sentence. So Bill claims that John admires himself cannot mean that John is admiring Bill. The indexes or subscripts or number are illustrating the possible meanings these sentences may have. So sentence 1, both John and himself have the same index 1, which means that they have to refer to the same person. And in the second sentence, the interpretation where this pronoun himself refers to Bill, number 1 or person 1 is marked as impossible. So we see that reflexives have some kind of locality property. They must co-refer or refer to the same entity as the subject of their own clause. The pronouns, regular pronouns like him, have the opposite profile. So John admires him. It cannot really mean that John is admiring himself. So the him has to refer to some third party. And then Bill claims that John admires him. Now we see that actually it is possible that him refers to the Bill. So John, it could be that John is admiring Bill. So this Bill is in the same sentence, but it's just not the local subject. So this is what we are dealing with when we are looking at binding. This is a typical binding data. And although there are many linguists who think that this phenomenon has to do with syntax, or perhaps it has to do with the interface between syntax and semantics, this really doesn't matter here, because what we are seeing here and what we are looking at here are fundamentally some type of co-reference relations. So something is regulating the way how referential expressions can pick up or refer to entities outside of language itself. And we want to work with this type of data. And so I will put aside the question now what binding ultimately is. I will be just using this as an example of working with semantic phenomena, for which it's not at least trivial, completely trivial, how should we approach this data. Now, there are two things we have to pay attention here. The first is how do we add this kind of semantic phenomena into our model? And that's relatively easy to answer, at least in principle. And the answer is, and this is the model that I'm using in my own research, this binding is something that comes from my own recent research work, not yet published, but possibly soon. So we will simply add the semantics, the semantic interpretations into the model as an additional representational system. So in other words, we have the phrase structures, which create syntactic structures behind expressions. Then we have the linearization and the post-syntactic function, which creates the surface sentences. But another part of the post-syntactic function is semantic interpretation. And the semantic interpretation takes these phrase structures as input and then creates semantic attributes for them. Attributes like what are the arguments, who is the object, what is the object, what is the subject, agent, patient, thematic roles, aspect, clause types like interrogativization, and binding. And binding involves the ways in which these expressions or some constituents in the final phrase structures refer to the representations, mental representations of the ultimate objects or persons that may or may not exist in the real world outside of our mind. I have actually no idea whatsoever how we could model the actual relations between our mental representations and objects in the real world, how we could do that in a computational domain, Pythons, for example. No doubt that it will be attempted and that can be done, but right now I have very few ideas how to approach that. But we are not interested in this here. All we need is some way of mapping syntactic representations into semantic representations. So that's one thing. And then we need some way of verifying that these mappings are correct, that they match with the attested behavior and attested semantic interpretations that we can elicit from native speakers. And one way to do this, and that's the way how I'm doing it. Well, first of all, I want to mention that it's possible. Let me go back a few sentences. The output of the model will obviously have to report all the semantic attributes that our theory is trying to predict. So that is taken for granted. The file or the log files and the other output files generated by your supervision layer will also have to report all the semantic attributes that your theory is pretending to predict. So when it comes to binding, the model I'm currently using, it will report a list of semantic objects that were projected into existence when the sentence was processed. In this case, the persons corresponding to John and some person corresponding to him and himself and all other referential expressions. So the output will contain a list of kind of ontological objects that these sentences are talking about. And it will also provide their properties. For example, him is assumed to is corresponding to an entity that is a human, male, and animated, and was there something else, singular, and third person, things like this. So we can, and then the output also contains the mappings. So we have a list of objects in the semantic space, as I call it, or these are simply representations of objects that the speaker or hearer is assuming that must exist. And then there is a list of another section in this log. There is a list of objects. Sorry, there are a list of constituents, referential constituents like John and him, and then information concerning how they can be mapped into the semantic objects, into the ontology. And these mappings are regulated by binding, so that John admires himself. The mapping is always so that whatever object John refers to in the ontology, himself will have to refer to the same thing. So that's a kind of trivial requirement. But the question then is, how can we verify that this is all correct? Now, we can begin by using simply manual verification. So you feed the same expression to the model, and it provides a list of semantic interpretations it's creating. And then you simply match the output with the observed facts yourself. You do the matching yourself. And this works in the beginning, but eventually it will become useless, because when there is several expressions, for example, in this dataset we have many hundreds of sentences illustrating different binding conditions. So it becomes impossible to check them manually every time I make a change in the theory. And we can imagine that in the future, this kind of datasets, they will have thousands of sentences. And even if we have few sentences, if they are from a language that I'm not a native speaker of, I can't do this checking manually. And even if I could, it's too slow and it's not reliable. So the manual checking works in the beginning, but doesn't, in the end, it will not work. So we need some way of doing the checking automatically. And the solution to this problem is, my view, also quite simple in the end. So the solution is that these semantic attributes that we are trying to predict, we can simply collect them into one data structure, dictionary, for example. So there will be a dictionary entry for binding, for example. One key is binding, and in the dictionary that key will map into the output. I'm talking about each expression at the level of each individual expression. And then we settle on some notation that we use to represent or express these semantic facts. Some type of standard notation, how we encode binding. And I already showed that there was, in these examples, we used the subscripts, the numbers. So that provides a very useful starting point. In other words, after you calculate the binding facts or the co-reference dependencies, whatever they are, you then transform those facts into some standard notation. Perhaps you use some kind of subscript notation. Doesn't really matter what it is. And in this dictionary where we produce all the output from the model, we then use that notation. I using myself simple strings. And now, after we reach this stage, we can then add these outputs into the data set. So we can tell that this is the expression, and then we provide below, for example, this expression a list of any semantic attributes we want to be verifying from this output dictionary. And then we write the string as it should be, as it would correspond to the reality, observed reality. And here is an example from my own dataset, what had to do with binding in Finnish, but I have here English examples for reference. So what's going on here is that this is the sentence in my dataset. It's supposed to evaluate as grammatical. And this notation here tells that I'm interested in some output attributes, semantic attributes. And it's followed by the key in the output dictionary where I provide all these output values, what I want to predict. In this case, I'm interested in binding. And then this is my own notation that I'm using currently. So we have all the referential expressions marked by, I use letters and not numbers. A, for example. So this is same as in my example where I had the John and the subscript 1. So here we have John and a subscript A in this notation. I can put subscripts into this regular text file. And I'm using a notation that if these two referential expressions are necessary, denote or refer necessarily to the same thing, as is the case in this sentence, then they will have the same index or subscript letter. This is just an arbitrary notation for binding facts and nothing special. And if the referential expressions are necessary, cannot refer to the same object in the ontology or semantic space, then they have different letters. And if they can refer to the same element but can also refer to something else, then there are several. Sorry. I hope that that was visible in my example, because I was not looking what is in my screen. So here we have the example, we have a notation that this him can refer to Bill or somebody else, third person, but it cannot refer to John because this index P is not in this list. So this is a way how I can add binding data into the data set. And then how I can automatically check whether my binding theory gives me correct predictions. And here is I conclude with another simple example. I'm testing here something else. I'm testing here whole conversations. It's possible in my model to feed it with multiple sentences which all rely on the same ontology. And I'm testing it here. So I'm basically introducing here another person, Tim, and then I will present a sentence, John admires Bill, and I am then verifying that the conversation and the ontology and the semantic system works correctly. But instead of using some kind of very complex formula to list all the possible ways these three names can be mapped into the three persons that are in the ontology, I will simply check that the number of assignment is one way of providing each referential expression some interpretation in the ontology. I'm just checking that the amount of assignment is correct. So here I have the same notation. We are testing a semantic attribute. The attribute is number of assignments, and this is something the model calculates or provides as output. and this is the number that we should have. And if my algorithm for conversations does not work correctly, then usually it means that this number that comes out of the model is not 6 but something else. And I can, by using this system, verify a huge amount of verify my model against a huge amount of binding facts automatically and in a way that is completely error-free. And this method works in connection with any attribute that I produce from the model. I can add into this data set. I just use this symbol. I'm telling that this is not a sentence, but this is a semantic attribute like binding. And then I will provide use the special notation I have created. So, in other words, I can test the model against any attribute I want. Thematic roles, quantifier scopes, aspect, tense, clause typing, predicate argument pairs, control, discourse features, clitics and critic combinations and their semantics. At least those I have in my current model. So, in conclusion, it's not really difficult to work with semantics in principle. The difficulty, as usual, is to get all this data correct. But in principle, we simply stipulate some notation that we use to model this semantic interpretation or aspects of semantics. And once we have this format, we can use the same format and add the semantic attributes to the dataset and check them against the model.